we are given 5 statements and we need to determine which of the following statements are false. So the answer is 1, 2, and 4. So first, second, and fourth statements are false. And let's look why. So statement 1 says that if the number of equations in a linear system exceeds the number of unknowns, then the system must be inconsistent, no solutions. Well, let's look at example. For instance, x equals 8, so number 1. X equals 8 and 2x equals 16. So this is a system of equations and it has only one solution, that x equals 8. But this system proves that our statement is false because it's not compulsory that if the number of equations in a linear system exceeds the numbers of unknowns, that the system must be inconsistent. In this example, the number of equations is 2 and the number of variables is 1. That is, the number of equations is exceeded by the number of variables, but the system is consistent. Well, now, so number 1 is false. So let's look at number 2. So for number 2, if matrix B, let matrix B be 2 by 2 matrix with a column with 0, so it can be A, 0, B, 0. Or actually, let's call its entries as B1, B2. And then matrix A has entries A1, A2, A3, A4. Let's try to find their product AB. So AB equals matrix A times matrix B. So we will have A1 times B1 plus A2 times B2. Next entry is A1 times 0 plus A2 times 0. Here we have A3 times B1 plus A4 times B2. And here it's A3 times 0 and plus A4 times 0. So as you can see, the second column of product matrix AB equals 0, which proves that the given statement is true. A4B2. The given statement is true, and if one of the matrices has a column with zeros, then the product of these matrices will also have a column with zeros. Okay, now let's move on to statement number 3. If AB plus BA is defined, then A and B are square matrices of the same order. So here what you need to remember is that if you multiply two matrices A and B, and for instance order of matrix, so first of all, when we find the product of matrices, the number of columns in the first matrix needs to be equal to the number of rows in the second matrix. So if we are able to find product AB, that means that the number of columns, for instance, the number of rows in matrix A is n, number of columns is m. That means that the number of rows in matrix B is also m. Let it be some k, yeah? So A is n by m matrix, B is m by k matrix, so AB is defined. However, since BA is also needs to be defined, that means that the number of columns in matrix B equals the numbers of rows in matrix A. So we get that A is n by m matrix and B is m by n matrix. So n equals k, so that BA is defined. But now in order to find the sum of AB and BA, AB and BA need to be of the same order. So for instance, when you find matrix AB, if A is n by m matrix and B is m by n matrix, so their product will, the order of the product will be the number of the rows of the first matrix by the number of the columns of the second matrix. So here we get n by n matrix, yeah, and then the order of BA is also the number of the rows of the first matrix, which is m, by the number of the columns of the second, which is also m, so m by m. But we know that they are of the same order, so that means that n by n needs to be the same to m by m, so n equals m. So we get that A is n by n matrix and B is also n by n matrix. So we have proved that they both need to be square matrix of the same order. Wait, AB plus BA is defined. Well, now let's move on to number 4. Number 4 is not true, it's false. We can prove it by providing an example. So basically number 4 states that if A is n by n matrix and A squared equals 0, where 0 is a 0 matrix, then this means that A is a 0 matrix. Well, let's try to find a counterexample for this. So number 4, consider A be equal 0, 0, 1, 0. So as you can see, A is a non-zero matrix, but then if you want to find A squared equals A times A, so it equals this matrix times this matrix again. Now let's try to find this product. So the first entry is 0 times 0 plus 0 times 0 times 1. Then we have 0 times 0 plus 0 times 0, 1 times 0 plus 0 times 1, and 1 times 0 plus 0 times 0. So as you can see, the first entry is 0, the second entry is 0, here we have 0, 0. So the A squared is a 0 matrix, while A is not. So that proves that statement number 4 is false.